Hi, Algebra 2 Honor students. We're up to Unit 7, Day 3, which is going to be about sum and product of the roots. Today we're going to look at, there's a connection between, when we talk about the roots of the equation, right, those x-intercepts, there's some connection between the sum of those roots and the product of those roots and how they fit into the actual equation of the quadratic that we're looking at. So we're going to actually generalize this right away at the start of the lesson to get an understanding of what sum and product of the roots are all about. So we're going to say, given the roots of a quadratic are R1 and R2. Just in general, root 1, root 2 are two given roots of a quadratic. What would its linear factors be? Okay, so linear factors are what factors produce these solutions of R1 and R2. So if you're unsure about what I'm talking about, the linear factor that gives you a root of R1 is x minus R1. It's the binomial that when you set to 0, if you solve for x by adding the R1 to the other side, that's the root that we're talking about there. And therefore, the other linear factor would have to be x minus R2. So since we're talking about an equation, we really need to make sure we set this equal to 0, such that if I were to set each of these factors to 0 individually, we get those two roots. So what do I want you to do with this information? I want you to multiply it out. I want to see what quadratic is the result of multiplying these two things together. So you could do box method, you could do FOIL, and I know I probably usually default to FOIL just because when I was a student, that's how I learned it. Box method was like not a thing yet. When that's how old I am. Box method probably wasn't invented yet. I mean, it was always around, I guess, but it just wasn't the way that I learned it as a student. So x times x is going to be x squared for the first term there. And then the outside would be minus x times R2. The inside product would be minus x times R1. And at the end, negative R1 times negative R2 is now positive R1 times R2. And that equals 0. So this doesn't mean a lot to us probably quite yet. We're looking at it, we're like, okay, who cares? We multiplied it together. But something really interesting happens when you take a look at kind of what's going on in the middle there. So what's happening in the middle is that these are my x terms. And if we take that x out of things as a GCF, what we're left with is negative R1 and then minus the R2, right? If I take an x from each of these, we have negative R1 and negative R2 left over. And because both of them are negative, what we can do is we can even take out a negative from that quantity, right? If I take negative R1 minus R2, if I pull out a negative, now it becomes R1 plus R2 as the coefficient of x. And at the end, we get plus R1, R2, and that still equals 0. If you don't believe me, of course, you could distribute that negative back in and then distribute the x backwards, and it's going to get you right to this. So why did I want to rearrange it that way? Well, take a look at what's happening here. In the middle for this coefficient of x, we're going to take the negative sign of whatever the sum of the roots are, right? R1 plus R2 means add the roots together. And apparently, at the end, R1 times R2, that's the product of the roots. So in general, a quadratic equation can be determined based on the sum and the product of its roots. So we can write this as x squared, the opposite sign of the sum of the roots times x, plus the product of the roots would equal 0. And that's pretty great because that means that if I gave you the roots, we can generate the equation of that quadratic really easily. Okay. So to get some practice with this idea, if I gave you roots of 3 and 5, let's start with kind of nice, easy numbers. The roots are 3 and 5. Well, if I really quickly off to the side find the sum of the roots, 3 plus 5, that's 8. And also find the product of the roots, 3 times 5, which is 15. What I'm saying is that using the sum and the product there, we know what equation would generate these two roots right here. So it's going to be x squared. We're going to change the sign of the sum. It's the opposite sign of the sum. So it's minus 8x plus 15 is equal to 0. This quadratic has these two roots, 3 and 5. And if you don't believe me, there's a couple things you could do. I guess you could either factor this and see if you can get those roots again. Or why don't we check by creating those linear factors like we did up here, right? So if we have roots at 3 and 5, the linear factors would come from x minus 3 times x minus 5. Okay, so if I set that to 0 and I multiply this together, will I get this result again? I don't know. Let's see. So we're going to get x squared. The outside is minus 5x. The inside's minus 3x. And then the last term would be a plus 15 there. So combining like terms in the middle, x squared minus 8x plus 15 is the result, which of course, you never doubted me, right? That is the exact equation I got from using sum and product right there. So notice how quickly we can generate the sum and product to get this result. And maybe you were thinking it was just as easy when the roots are nice numbers like 3 and 5 to get x minus 3 and x minus 5 there. But I promise you, when the roots get a little bit more complicated looking, we're going to want to have this idea with sum and product. So if the roots were negative 2 and 7, we can do something just as easy, right? So the sum would be negative 2 plus 7, which is a total of 5. The product would be negative 2 times 7, negative 14. So altogether, the equation of the quadratic would be x squared, change the sign of the sum, minus 5x, and then keep that product sign, so leave it minus 14 is equal to 0. Okay, so this is looking pretty good for us so far. Let's try another example where maybe the roots get slightly more complicated. All right, so how about we move on to the roots are 3 plus or minus radical 5. And number 4, the roots will be 4 plus or minus 2i. So we need this sum and product for roots that are irrational or roots that are complex like this, because what linear factor gives you this root? The answer is really no linear factor would give you either of these roots. When you get roots that look like this or look like this, it doesn't come from factoring. It comes from either quadratic formula or completing the square. So it's really important to have this rule with the sum and product of the roots to be able to establish what the equation of the original quadratic is. It's kind of like we're working backwards, right? Sometimes I give you the equation, we're asked to find the roots. Now, if I tell you the roots, we can use the information to work backwards. So if I add those up, the radical 5s nicely cancel. You'll never have a quadratic with a radical as a coefficient, by the way, so that should happen nicely, that those radicals cancel out. And I guess what that additionally means is that when I multiply these together, 3 plus radical 5 times 3 minus radical 5, that we shouldn't have a radical as that in that result either, which, because these are a conjugate pair, that will hold true. Okay, just a shout out for my box method fans of the crowd here. I'll do 3 plus radical 5 across the top, 3 minus radical 5 on the left column here, and then 3 times 3 is 9, and then we're going to get a 3 radical 5 over here. This product would be negative 3 radical 5. Negative radical 5 times positive radical 5 is a total of negative 5. So notice how, because they're conjugate pairs, these terms cancel out, and we're left with 9 minus 5 for a total product of 4. So if we have a sum of 6 and we have a product of 4, the equation would be x squared, change the sum, minus 6x, plus 4 is equal to 0. Okay. Moving over to the other side, really similar process, right? I've never seen a quadratic equation in my life that has i's as part of the coefficients. So when I separate those roots and I write the sum, those I parts cancel just like the radicals cancel over here. So we get a sum of 8. Thinking about the product, if I multiply those conjugate pairs, 4 plus 2i and 4 minus 2i, okay, I'm going to go back to my FOIL. And in fact, because I know the pattern already, because we've done this many times, I know that I really just have to do the first minus the last product, because that's going to give me I know the inside terms would cancel if I do the whole FOIL. So that's going to be 16 minus 4i squared. But of course, we know I squared is negative 1. So 16 minus 4 times negative 1 becomes 16 plus 4, better known as 20. So we have a sum of 8, we have a product of 20, so the equation would be x squared, change the sum, minus 8x, plus 20 is equal to 0. All right, I hope we're getting the hang of this so far. We're going to add in one that is everyone's favorite. What about roots of 4/3 and negative a half. I'm pretty convinced that you're going to like these examples better in the end than you're going to like this example, because you're looking at them and you're like, okay, well, there's no radicals, there's no i's there. However, when you go to find the sum of the roots, how do I add 4/3 plus negative a half? Well, we need a common denominator to do that. Can't just add those fractions if they don't have the same denominator. So the common denominator here is going to be a common denominator of 6, right? So multiply this one by 2/2, this one by 3/3. So we wind up getting 8/6, and then plus negative 3/6 for a total of 5/6 for the sum. All right, so that's not the worst thing. I mean, we can get common denominators. We should have good enough fraction skills in this course that we don't have to worry too much about that. But maybe it's been a while since we've had to add fractions. Okay, 4/3 times negative a half, on the other hand, you don't need a common denominator when you're multiplying fractions. You get to multiply across the top and across the bottom. In fact, you can even do some cross canceling here. Don't ever do that over here, by the way. You have to get a common denominator when you add and subtract. But 2 goes into 4 twice, so if you want to reduce that, 2 times negative 1 across the top is negative 2, and then 3 times technically 1 on the bottom is 3. So we get a sum of 5/6 and a product of negative 2/3, which makes my quadratic equation x squared, change the sum, minus 5/6x, and then keep the product minus 2/3 equals 0. And I'll tell you, even when I write this equation, typically you don't see quadratics that look like this either. Usually the coefficients in a quadratic are what we call integral. Integral meaning that they're integers, not fractions. Like, these are rational values, but they're not integers. So in the directions, typically a question of this form would say express with integral coefficients, meaning that we need the coefficients to be integers. So what you're going to do is you're going to look at those two fractions that we have in the equation right now, and you're going to ask yourself, what is the LCD of those two denominators? And I hope you would really quickly come up with an LCD of 6, right? If I multiply this one by 2, I can get the LCD of 6, and that's already 6. So in fact, what I'm going to do once I've decided that the LCD is 6, I'm just going to multiply both sides of the equation by 6. Notice how we kind of like that this is going to change the fact that it's still equal to 0 on this side. But when I distribute the 6 over here, it's going to eliminate those fractions. So the equation would be 6x squared. When I distribute it to the middle, the 6's would cancel to get negative 5x in the middle. And then just be a little bit careful at the end. 3 goes into 6 twice. And then 2 times 2 would be minus 4 at the end of the equation equals 0. And that should look a lot nicer to us. And if we were to factor this into the appropriate factors, we're going to get solutions of 4/3 and negative a half, which is pretty awesome. And if we're not like too keen on factoring to check, you could always plug it in the calculator, double check that it crosses the x-axis at negative 1/2 and positive 4/3. So yeah, fractions, maybe they're not as easy to contend with as even sometimes complex roots or irrational roots, but they're also not the worst thing either. We can handle them pretty easily. Okay. So what we should see is if we look at this example here, what was the sum of the roots? It was 5/6. So we have to be cautious that when we look at an equation, I can't just look at the middle term and say, oh, that's the sum, or it's the opposite sign of the sum at that, right? The sum of the roots is not positive 5, it's positive 5/6. And the product of the roots is not just necessarily the last number, it's this number divided by 6, because negative 4 divided by 6 is negative 2/3. So we didn't really have to account for that until I give you an equation and I ask you for the sum and product of the roots. Okay, so given a quadratic in standard form, if we have ax squared plus bx plus c equals 0, okay, that is the standard form of a quadratic. If I asked you, what's the sum of the roots in general? Well, the sum of the roots is not just the opposite sign of this coefficient, but it's the opposite sign of b divided by that lead coefficient of a. And in a lot of our cases, a might wind up being 1, so that's fine. But if a is not 1, we have to take that into account, just like the last example we saw. And therefore, if we think about the product of the roots, we can't just say that the product is the last coefficient, c. And by the way, we keep this sign for the product always. But it winds up being c divided by a. And I know some of you will like this reference, okay, if you're a basketball fan at all. But a good way to remember this is we have S equals negative B over A for sum, right? Product is C over A. And this is just something that I actually heard a long time ago, and some students like it. If you like it, go for it. But I'm going to say that some NBA players can alley-oop. And if you have no idea what I'm talking about here, no big deal. Okay, but what is this even referencing? It's meaning that the sum of the roots equals NBA negative B over A. Some NBA players product can alley-oop C over A. If this is a way to help you remember this phrasing, I don't think you necessarily need it, but if it's a way just as a quick little, oh yeah, some NBA players can alley-oop, you know the sum and product of the roots formula. And the great thing is that N even tells you negate the B over A quantity. So that's kind of a nice way to remember that rule, but I don't think you'll necessarily need it. So no big deal there. All right, let's put this into practice real quick here. So if I gave you some equations, I'm going to give you a couple equations. And once I give you the equation, you'll tell me the sum of the roots and the product of the roots. Okay, so let me write the equations first. Let's do x squared plus 3x minus 2 equals 0. Two x squared minus 5x plus 4 equals 0. And then the last one we'll do is x squared minus 3 equals 0. Okay. So we should be able to do this really fast, shouldn't we, right? If we know the rule that the sum is the opposite of the middle term over A, the product is C over A. Well, the nice thing about the first one I gave you is that the value of A is 1. So the sum of the roots given this equation would be negative 3, technically over 1, but we don't have to write that. And then the product would be keep the sign of the last term, so negative 2. Sum is negative 3, product's negative 2. Moving on to the second equation, 2x squared minus 5x plus 4. The sum is the opposite of this number, so 5, but oops, divided by 2. Don't just write 5, but it's 5 halves. B over A. Okay, the product would be C over A, so the product would be 4 over 2, which is just 2. Easy enough. And for the last example, the sum of the roots would be, well, the lead coefficient's 1, which is nice, but wait, there's no x term in the middle. And I know you guys noticed that as soon as I wrote it down. Well, the sum of the roots is 0 then. Means if I add up the roots that they must add up to 0. And then the product would be still that last coefficient of negative 3 divided by 1, which is still, of course, negative 3. So we should be able to do that pretty easily. Okay, last thing I'm going to tell you is we're going to work on somewhere we're given the sum and product. We're going to write the equation of the quadratic. And we'll do sum equals negative 3, product equals 4. We'll do sum equals 8, product equals negative 20. And I'll even throw a crazy one in for us. How about sum equals negative 2, product equals 5/7. We'll go with that. Okay? So these are the last ones that we'll do. Given the sum and product, we'll write the equation of the quadratic that has a sum of the roots equal to negative 3, product equal to 4. All right, so here's what we're going to do. First one. If the sum is negative 3, it's going to be x squared plus 3x, right? Change the sign of the sum. Keep the product plus 4 equals 0, and we are done. These go so fast, you're going to love them. All right, sum is 8, product is negative 20. The equation is x squared. Change the sum, minus 8x. Keep that product, minus 20 equals 0. Done. And last but not least, sum of negative 2. We saved the best for last, didn't we here? Maybe, I don't know. Okay, so it's x squared plus 2x, right? Change it. Keep the product of 5/7 equals 0. But oh no, we can't leave something with non-integer coefficients. We need integral coefficients. And since there's only one fraction here altogether, the LCD is definitely 7. So all you have to do to fix this, and I would expect you to do that, it's going to say to do it in the directions, is multiply both sides by 7. So then we get 7x squared plus 14x in the middle. If I multiply this by 7, now it turns into a plus 5 at the end equals 0. Hey, and double check, is the sum of the roots negative 2? Negative 14 over 7? Sure is. Is the product 5 over 7 the product? Yeah, absolutely. So multiplying by 7 just cleans it up, makes it look a little bit nicer, and it still holds the same sum and product. Well, we're going to have a great recap of this lesson next time I see you. Here's quadratics day 3. Have a great rest of your day.